So once chemists started looking at all the data for this kind of stuff and started putting these together, they had to come up with a new convention to balance electrochemical reactions, because there's a little bit more going on than the normal balancing of chemical equations we did back in chapter 4 of our textbook. So to illustrate this example, we're going to balance the following reaction in an acid medium. And the particular reaction that we're going to balance is Cr2O7 2 minus in aqueous solution plus C2H5OH as a gas. This is going to give us Cr3 plus in aqueous solution plus CO2 as a gas plus H2O as a gas. So here's our particular overall equation. This should make sense that the chromium is going from Cr2O7 2 minus to Cr3 plus, because one of the things that we have to look at in these particular oxidation reduction reactions is a section of chapter 4.4 where we talk about assigning oxidation states to various species in a particular reaction like this. If we're going to assign oxidation states, the two most common rules are hydrogen in a species, unless it's in elemental form, has an oxidation state of +1. Okay? Oxygen would like to have an oxidation state of -2, and the exception of that is if it's a peroxide. So in most cases, we can look at all the hydrogens and look at the oxygens first. And the transition metal oxidation states vary, and we can look at the other species in that particular compound. Another thing we have to look at is if I have a particular compound or ion, the sum of the oxidation states have to add up to equal the charge on that particular ion or compound. If an ion, like in this case, has a -2 charge, the sum of the oxidation states has to add up to -2. If the molecule is neutral, the sum of the oxidation states have to add up to 0. So we know in this case that for this dichromate, or Cr2O7, that oxygen has a -2 oxidation state, and there's 7 of them. The total oxidation state of this ion has to be -2. So we know that 2 times the oxidation state of the chromium plus 7 times -2 has to equal an overall charge of -2. So 2 times the oxidation state of chromium has to equal +12, and in this case, chromium is going to equal +6. So in this particular species, chromium has an oxidation state of +6, oxygen -2. If we do the same type of analysis for everything else, the oxidation state of hydrogen in this alcohol is +1. There's going to be +1 times 6 for the hydrogens, +1 times -2 for the oxygen. And this has to equal 0 since this is neutral. And we have 2 times the oxidation state of carbon plus 6 minus 2 is going to equal 0. So in this case, the carbon has an oxidation state of -2. So here our carbon is -2. If we have a species like chromium as an ion in solution, its oxidation state is equal to the charge on the ion. So the chromium here is going to be +3. In CO2, the oxygen is going to be -2, and here the carbon must be +4. And then with the water, hydrogen is going to be +1, oxygen's -2. So in these particular cases, unless you have oxygen as a peroxide or as O2 gas, its oxidation state's going to stay fairly constant. Okay? We have the chromium being reduced from +6 to +3, and we have the carbon being oxidized from -2 to +4. So this is what's happening in this particular reaction. So we can break this down into a reduction half cell and an oxidation half cell. Because we have to do this for these particular reactions because it's hard to be able to analyze this just by looking at the particular equation and throwing around different coefficients in front of each of these. So in our reduction half cell, we have Cr2O7 2- being converted into Cr3+. In this particular case, the first thing that we always want to balance is our transition metal. So if we have Cr2O7 2-, we need a 2 in front of the coefficient here for the chromium 3+. In this particular case, we're in acid medium, so to balance out the oxygens, we need some water. So we're going to need 7 waters over here on the right-hand side for this particular half reaction. By doing so, we're going to need 14 hydrogens over here on the left. So here we have 2 chromiums on the left, 2 chromiums on the right, 14 oxygens on the left, 14 oxygens on the right. Sorry, 7 oxygens on the left, 7 on the right, 14 hydrogens on each side. So we have everything good to go for this particular half reaction. We now need to make sure we balance out the charges. We have 2 times +3 or +6 over on the right-hand side, and we have +14 and -2 on the left. So we have a +12 charge on the left, a +6 on the right. So we need to add 6 electrons over here to the left-hand side. In our oxidation half reaction, we have C2H5OH as a gas, becoming 2CO2 as a gas. So in order to balance this out, we need to look at where we need to add our waters and where we need to add our hydrogens. To balance this particular reaction out, we have 4 oxygens on the right, only 1 on the left, so we need 3 waters over here. If we add 3 waters, we have 6 + 6 or 12 H+ on the left, so that means we need 12 H+ over here on the right. To balance out the charges, everything is neutral with the exception of the H+, so we need 12 electrons over here to balance everything out. In order to balance the overall half reaction, we need to make sure our electrons cancel out. So we need to multiply the reduction half reaction by 2. So that will give us an overall reaction that's the following. We're going to have, if we multiply all this out, 28 H+ in aqueous solution plus 2 Cr2O7 2- ions in solution plus 12 electrons plus 3 waters plus C2H5OH as a gas. This is going to give us 4 Cr3+ plus 14 waters plus 2 CO2s plus 12 H+ plus 12 electrons. In this case, the 12 electrons cancel out. In the particular overall half reaction, we see a couple species showing up more than once. We can cancel those out. if we have 12 H plus on the right and 28 on the left, we can cancel these 12 out, and instead of 28, we'll have 16 here. We have 3 waters on the left and 14 on the right, so these 3 will cancel out with 3 of these to give us 11 total. And our overall half reaction in acidic medium would be 16 H plus in aqueous solution plus 2 Cr2O7 2 minus plus C2H5OH. This is as a gas, giving us 4 Cr3 plus in aqueous solution plus 11 waters plus 2 CO2 as a gas. Now, looking at this overall reaction down here compared to what we were given initially, it would be very hard for pretty much all of us to try to look at that and be able to distinguish how many electrons are being transferred, how many waters we would need, and how many H pluses we would need. So in order to get to this, we need to break this down into an oxidation half reaction and a reduction half reaction. There are 2 different ways that we can be asked this particular question. This first one right here is if we balance the reaction in acidic solution. We can also be asked to balance this same chemical reaction in basic solution. The only main thing that changes when we go from an acidic solution to a basic solution is the fact that in a basic solution we will never have H plus ions floating around in there. We'll have OH minus ions. So what we have to do to get to the basic solution balancing is anytime you see an H plus, we need to neutralize that with an OH minus. So for example, we have this H plus right here. We need to neutralize that with 16 OH minuses. So in doing so, if we neutralize this, we're going to get 16 waters. If we add 16 OH minuses to the left-hand side of the reaction, that means we also have to add 16 OH minuses to the right-hand side of the reaction. So by adding these waters and adding these hydroxides, we can cancel a few more things out. So in this case, we have 16 waters on the left, and we have 11 over here on the right. So to balance this in basic solution, we're going to get the overall reaction that is 5 H2O as a liquid, plus 2 Cr2O7 2 minus in aqueous solution, plus C2H5OH as a gas, giving us 4 Cr3 plus in aqueous solution, plus 2 CO2s as a gas, plus 16 OH minus in aqueous solution. So this equation right here is our balanced solution, or balanced equation in basic solution. So the way I like to approach these problems is when it says balance the following electrochemical reaction, first assume that it's in acidic conditions and go down and balance it with the H pluses and the waters on either side. Then the next step, if it tells you, and then if it asks you for an acidic solution, you're done. If it asks you for basic, you kind of have to go one step farther and neutralize out all of the H pluses. So typically when you balance these equations, this is the method that you're going to use.